This part of our chapter deals with reactions that are known as oxidation and reduction reactions. This is probably a brand new topic to most students listening to this lesson. Redox reactions, that's the short word for putting together oxidation and reduction. They're commonly called redox. This is a very common type of chemical change where it's an umbrella of many other recognizable patterns. A redox reaction could also be a type of combination reaction. It could also represent a decomposition reaction. It could fall with a single replacement reaction, and even the combustion pattern. So the last series of reactions with lesson 2 and lesson 3 were all double replacement reactions. We started with formation of a precipitate. We did the acid-base neutralization, making a water, and the last little bit there was all about gas formation, the 3 different driving forces of a double replacement. Now notice the next category called redox. I've listed all the other recognizable change, combinations, decompositions, single replacements, and combustion patterns all fall under this big umbrella known as a redox reaction. What do all of these 4 different patterns of chemical change have in common? Well, it all has to do with the transfer of an electron through the course of the chemical change. Ionic compounds are formed through the transfer of electrons. An oxidation-reduction reaction involves transferring electrons as reactants move to products. When we think about a transfer of electrons, what we're going to end up looking at is who changed their charge from the left to the right side of arrows. Change of charge. What changed the charge as reactants form products? And that will help us identify what was oxidized and what was reduced. Oxidation and reduction talk about a transfer of electrons. Now, just to remember ourselves, we talked about the Bronsted-Lowry theory of acids and bases, and we talked about that as being proton transfer, and the term conjugate pairs was set up with acid-base chemistry. This is just a side note. Conjugate pairs with acids and bases deal with proton transfer. Opposite of that, when we're transferring of electrons, tracking negative transfer, negative electrons, we're going to look at some redox. So as a step 1, before we can write any type of chemical equation that involves transferring electrons, we have to learn what are oxidation states. How do we go about assigning charges so that we can keep track of what's changed? Somebody became more positive as they lost electrons, and somebody must become more negative as they gained electrons. So we're going to begin this lesson by learning how to assign oxidation numbers. It's a simple bookkeeping method. It's not necessarily true of what we find in nature, but it works. So it's a bookkeeping method that we've organized as chemists to come up with a way of assigning these charges, these oxidation numbers, so we can track electron flow. So just a way of keeping track. We need to memorize the rules for assigning oxidation states. So let's begin top of page 11 in our notes, going through these rules one by one. Read them with me carefully, and we're going to make some side notes for each one. Rule 1 reads, the oxidation state of elements in their elemental form, the way we find them in nature in other words, is always 0. The elemental form of an element is 0. So, for instance, in nature, I would find sodium solid. Sodium solid would have an oxidation state of 0. Hydrogen is one of those lucky 7 diatomics. It is going to be oxidation state of 0. So any element written, an element is a symbol written by itself, not carrying a charge, gets assigned a 0. Keep in mind there are 7 naturally occurring diatomic molecules who also have an elemental form oxidation state of 0. Number 2, oxidation states for monoatomic ions are the same as their charge. Monoatomic, a single atom carrying a charge. So up here I said, here's sodium atom, oxidation state of 0. What if I had a sodium ion, oxidation state of +1? Ions only exist in aqueous solutions, so I automatically know these are aqueous. Hydrogen ion has an oxidation state of +1. Molecular hydrogen, oxidation state of 0. Hydrogen ion, oxidation state of +1. Chloride ion, oxidation state of -1, and so forth. So the oxidation state for the ions, as we find them on the periodic table and deduce their charge, match their oxidation number. Rule number 3. Oxygen is assigned an oxidation state of -2 in its covalent compounds, except as a peroxide. Then it is assigned a -1. Now this rule is extremely important. Let's take some time with it. Rule 3. Oxygen, we know when it forms an ion, is O-2. I'm going to tell you 99% of the time oxygen's oxidation number is -2. We have this rare exception, and it's worth noting because I see it appear on the AP exam almost yearly. The exception is if we have a peroxide. This is known as oxide ion. What is a peroxide ion? Well, it gives us an example, Na2O2, sodium peroxide. Here we have barium, Ba, was it barium? Let me peek up again. Nope, it was hydrogen peroxide, H2O2. Now I know sodium's a +1, oxide must be a -1, but there's 2 units of it here. So this is just a little bit weird, isn't it? The overall charge here is -2, and that's why we come down and bring that 2. So the peroxide ion is O2, -2. So if I deduce that, give it to the lowest whole number ratio, the overall charge is -1. The peroxide, this is confusing, so I'm really going to try to stress this. This is peroxide. The ion is O2. It overall carries a -2, doesn't it? Because 2 units of a -1 give me an overall charge of -2. -1, 2 of them there, gives me a -2. Since barium's a +2, the compound barium peroxide, BaO2. The compound barium oxide, BaO. So please make yourself a note. This is a rare exception. Peroxides, you're going to notice that it just looks odd to you. Why don't we reduce this down? Well, peroxide itself is O2 carrying a -2 charge. So therefore the single atom of oxygen in a peroxide carries a -1 overall. Rule 3, so important. 99% of the time oxygen is a -2. Once in a great blue moon, we have a peroxide, sodium peroxide, hydrogen peroxide, barium peroxide, and so forth. Rule 4. Hydrogen is always assigned a +1 when bonded to a nonmetal and a -1 when bonded to metals. Another critical rule. Memorize. Let's discuss it to help it kind of sink in. So rule 4, here was rule 3. Let's talk about hydrogen. Oops, rule 4 is what I meant to write. It says if hydrogen is written in the first position, bonded to a non-metal, HCl, I'll do H2S, just based on charge, +1, -1, +1, -2. If I have hydrogen written in the first position, bonded to a nonmetal that carries a negative charge, hydrogen is a +1. This is called the hydrogen ion. Now the flip side of that rule says, What if hydrogen's written in the second position, hooked to a metal? Let's suppose I have NaH. This guy here is now carrying a -1 charge. This ion we learned is hydride. NaH, hydride. How about CaH2, calcium hydride? The charge on hydrogen written in the last position when hooked to a metal is -1. Hydrogen in the first position hooked to a non-metal carries a +1 charge. Rule 4 is reminding us that hydrogen can be a +1 or hydrogen can be a -1, simply depending on the substance it's hooked to. Rule 5, pretty straightforward, no exceptions at all. Fluorine, always a -1. The most electronegative element on our periodic table, always a -1. Fluoride, -1. Now remember, molecular fluorine, the way we find it in nature, 0. Rule number 1 review. Rule number 5 says if it's hooked in a compound, it's a -1 charge. Rule number 6. The sum of all oxidation numbers in a neutral compound is always 0. We've learned that when we try to crisscross charges, we make an electrically neutral compound. The sum of oxidation numbers in a polyatomic ion equals the charge on that ion. So for instance, let's suppose I have a neutral compound, NaCl, sodium chloride. The number of positives electrically balance the number of negatives to give us 0. Suppose I had a polyatomic ion, I'll just make up chlorate, ClO3, -1. The sum of the two oxidation states, one would come from chlorine, one would come from oxygen, their sum would give me -1 overall. By the way, what would the oxidation number of chlorine be? Rule number 3, oxygen is always assigned a -2. Always, always, unless it's a peroxide, and this is not. So the total negative 3 units here, 3 times -2, the total negative is -6. What must the oxidation number on the chlorine be so that when I sum the two numbers together, I get a -1? What, when added to -6, brings me to -1? Well, it's a +5, isn't it? The oxidation state on chlorine in this polyatomic ion called chlorate is +5. Now, chloride, Cl-, a monoatomic ion, its oxidation number is -1. My goodness, it changes depending on what it's involved with. Chlorine in this polyatomic ion is a +5. Chlorine in this binary ionic compound is a -1. That takes some practice, doesn't it? Let's assign oxidation states to each of the elements in the following, practicing the rules as we go through. Here we have carbon dioxide, CO2. What rule number might play a role here? Well, let's read. Rule number 3 about oxygen. I always start with the oxygen because there's a rule about it. It says oxygen is always assigned a -2. Oxygen is a -2 oxidation number. The total negative then is -4. Rule number 6 says when I sum these oxidation states together for a neutral compound, it ends up to be 0. So what must the oxidation number of carbon end up being so that when I add it to a -4, I land at 0 on the number line? Well, you've got it. Carbon must be a +4. A +4, when added to a -4, is a 0. Starting with the oxygen, we deduce the carbon from it. Let's try another. Here we have nitrate. Oh, maybe I'll just extend the page. That's probably easier. nitrate. NO3, -1. So here's an oxygen. We know that this is not a peroxide, so it's always assigned a -2. Oxidation state of oxygen is -2. 3 units of a -2, 3 times 2 gives me a total of -6. Now remember, this is a polyatomic ion, so the sum of the oxidation states will land at a -1. What must the oxidation number for the nitrogen be so that when I sum with a -6, I go to a -1 on the number line? A +5. The oxidation number of nitrogen in the polyatomic ion nitrate is a -1. How about H2SO4? Well, rule number 3, I like this one. It gives me an idea about oxygen. So oxygen is always assigned a -2. 4 units of a -2 give me a total of -8. This is a neutral compound, so I know that when I'm done, I got to add to 0. Here's hydrogen written in the first position. Rule 4. When hydrogen is bonded to nonmetals, it carries a +1. 2 units of that +1 give me a total of +2. What's the missing number that will be the oxidation state for sulfur? Well, we're going to need a +6. 2 units here, +6 gets me a total of +8. -8 lands me to 0. The oxidation number of hydrogen, +1. The oxidation state of sulfur, +6. The oxidation state of oxygen is -2. How about this one? Fe2O3. Well, the rule for oxygen, -2. 3 units of a -2 give me a -6. I know it will end to be 0 because it's a neutral compound. I know that the total positive has to be +6. To get me to 0, the total positive is +6. But notice I have 2 units of the positive ion. 6 divided by 2 gives me a +3. Iron's oxidation state is +3. Oxygen's oxidation number is -2. And friends, the last one is an error. Fe3O4 would produce a fraction. Could you just please cross that off? It doesn't work. Alrighty. After we cross that off, we have a you try it. What noble gas element has the same number of electrons as the fluoride ion? Well, the noble gas, of course, helium, neon, argon, krypton, xenon. So it's group 8A. Noble gases is the last column in our periodic table. If fluoride ion is F-1, find it on the periodic table, you'll notice that fluorine, element number 9, gains an electron. What noble gas does it become? It's right next door to neon, the end of row 2 on our periodic table. What is the oxidations number of that species? Well, neon oxidation number is an element in its natural state. Rule number 1, we know that it would not carry a charge at all. Fluoride has the same number of electrons as neon. Fluoride gained an electron, carries a -1 charge. Neon, a noble gas, would never gain or lose. Its elemental form gives us an oxidation number of 0. So important to practice assigning oxidation numbers. Let's try some more. First one we have is hydrogen sulfide. Hydrogen sulfide. Chemical formula is H2S. Rule number 2 at the top of our paper, oxidation number for hydrogen. It's rule number 4 dealing with hydrogen. Hydrogen is assigned a +1. So that gives me a total positive +2, making sulfur here a -2. Sulfur in hydrogen sulfide is a -2. Elemental sulfur, S8. This is commonly called flowers of sulfur. Well, here's the big key word right here, elemental sulfur. The way we find sulfur in nature is assigned a 0. Any element found in its natural state has an oxidation number of 0. Sulfur dichloride. Sulfur dichloride. Hear those prefixes? This is a molecular compound, isn't it? Knowing that sulfur dichloride is molecular, let's begin with chloride. Knowing where it lives on the periodic table is telling us it's a -1 charge. So the total negative here, 2 units of that -1 give me a -2 overall. So sulfur here must be a +2. First scenario, a -2, then a 0, now a +2. It's changing all over the place. Remember, this is just a way of bookkeeping. It's not anything to do but just bookkeeping. Sodium sulfite. Na2SO3, sodium sulfite. Oxygen rule, -2. 3 times -2 gives me -6 overall, coming from oxygen. Sodium in the first position we know to be a +1. 2 units of that give me a +2 overall. Always leave this middle one to figure it out last. What must be in this position to land at 0? Oh yeah, it's got to be a +4. Oxidation state of sulfur here is +4. And we have one more in our set, the sulfate ion. Sulfate is a polyatomic ion, SO4 -2. The oxygen rule tells us oxygen's a -2, so the total negative is at -8. Polyatomic will sum to give me their overall charge, so that's a -2 overall. What must I add to a -8 to end at a -2? A +6. Sulfur in the last example is a +6. Sulfur gave us an example of an element that changes drastically just depending on the type of compound it's found in. We're going to start working some examples of reactions that fall under this big umbrella called redox reactions. Remembering that what they all have in common, all these kinds of reactions, be it a combination reaction, could be a decomposition, could be a single replacement, and it could be a combustion pattern, not the double replacement. All of these 4 patterns fall under this large umbrella called a redox reaction. And what that commonality is between them is how they change charge. When reactants form products, we'll see that there have been a change in their oxidation state as reactants go to product. Now let's take an example of a combination pattern first. So a familiar pattern of a combination. Suppose we have a metal, Na for sodium, and it would be in a solid state, reacting with the elemental form of chlorine, Cl2, it's a molecular element, and it is in nature in the gaseous form. The pattern of chemical change for a combination reminds us that when a metal, such as sodium, combines with a nonmetal, such as chlorine, they're going to form an ionic compound and they're going to hook by charge. We had studied this very much in depth in our first year chemistry. They form a compound, an ionic compound, commonly called a salt, sodium chloride. Sodium with its plus charge, chloride with its minus, we get NaCl. Now remember, when we studied the 6 rules for assigning oxidation states, any element in its natural form, such as sodium, has an oxidation state of a 0. Chlorine, found in its elemental form as a molecule, has an oxidation state of 0. Now when they hook together, notice now how they're carrying a charge. The oxidation number of sodium is +1, and the oxidation number of chloride is -1. Sodium changed charge. It started as a 0 and became more positive. Chlorine went from a 0 and became more negative. We've had a transfer of electrons. Now let's go ahead and balance this. We'll need a 2 in front of each of these. So 2 NAs plus Cl2 makes 2 NaCls. You'll need to adjust that coefficient in your notepad page. So we've had a transfer of electrons. When sodium became more positive, let's show this. Sodium started at 0, became more positive. Now what has happened is it's lost 1 electron. Notice how a +1 charge, when added to the negative charge of an electron, gives me the 0. So the charges on both sides of our arrow are matching. They're both at 0. When chlorine started at 0 and went over to chloride, -1, well, it had 2 units of -1, we're going to see a total of 2 electrons being lost there. And you can see why we distributed the coefficient of 2 in front of each of the sodium, so that the number of electrons lost equals the number of electrons gained. We're going to practice this half reaction method multiple times. What we've just done is split the oxidation and reduction into 2 halves, the half reactions. We can label this process as oxidation and this process as reduction. The oxidation is a loss of an electron. Reduction is the gain of an electron. In this combination pattern, we saw sodium and the chlorine change charge, and they did so through the process of transferring an electron. Let's take a peek at a second pattern that's very familiar to us, called a combustion pattern. When a hydrocarbon combusts, our pattern of chemical change, let's take an example of a simple hydrocarbon called methane, CH4, adding oxygen, and a whole bunch of heat and light are produced along with carbon dioxide and water. Here is the skeleton of our combustion pattern. Let's go ahead and take a minute to balance. 4 H's, I think we'll need to double the water. 2 and 2, we'll need to double the oxygen. So here's our balanced combustion pattern. Now how might this also be labeled as a redox reaction? What has changed charge? Well, let's take a minute and use those 6 rules to identify what are the oxidation numbers of each of the elements. Here's an element in its natural state, molecular oxygen. Any element found in its natural state is assigned a 0. Over here, hydrogen, this is rule 4, I believe, hydrogen is attached to a non-metal, making it a +1. Carbon would have to be a total of a net 4 to sum to equal 0. 4 units of a +1 balance a -4. How about on this side? Oxygen's always a -2 unless it's a peroxide, but it is not here in this carbon dioxide molecule, giving me a total of -4. So carbon must be a +4. Hydrogen's +1, -2. So what has changed? Well, right away I noticed that oxygen started at a 0 and became more negative. It has gained electrons, becoming more negative by taking in more negative electrons. Carbon on the number line went from -4 all the way to +4. When you become more positive, you've lost electrons. Of course, the hydrogen did not change, and oxygen could have gone to either place. I could have gone either way, and south at it changed from 0 to -2. So with our very first exposure to redox reactions, we looked at a combination pattern and we looked at a combustion pattern. Both of these have a larger umbrella called a redox reaction that describes any type of reaction where charges or oxidation numbers change on an element from the left to the right-hand side are now going to be called combustion. So oxidation, that term oxidation, means an increase in the oxidation state, an increase becoming more positive on the number line. You do that by losing those negative electrons. Take away a negative particle and the resulting species is more positive. The term reduction means to reduce your oxidation number. You become more negative, and you do that by gaining those negative electrons. There's a little saying that helps me remember oxidation and reduction. Some teachers I've heard use the term oil rig. Oxidation is loss, reduction is gain. However, the one that I've always used is Leo and Gur. There's a funny little sentence. Leo the lion says Gur. Leo, loss of electrons, is oxidation. Loss of electrons is oxidation. And Gur, the gain of electrons, is reduction. Something that is oxidized has increased its oxidation number on the number line by becoming more positive. Something that is reduced has gained electrons and becomes more negative on the number line. Now, just to make this a little bit confusing, and I apologize for doing this, but we've got some vocabulary associated with this, and it is confusing at first, but kids will eventually kick it in. We have the term agent to describe. So let's go ahead and fill in the blank. Oxidation means an increase in oxidation state. Reduction means a decrease in oxidation state. But up here where it says, I'll go ahead and show the slide, the substance that is oxidized is called the reducing agent, and the substance that is reduced is called the oxidizing agent. Go ahead and fill those blanks in, and then let's go down and kind of give some clarification to those vocabulary words. Remember in our previous example where we had sodium atom losing an electron, and we wrote this out as an oxidation half reaction, a loss of an electron. Because sodium is being oxidized, it is called the reducing agent. The term agent means it's forcing the other reactant to become reduced. We had chlorine gaining 2 electrons. Let me add that back in correctly. Gaining 2 electrons to form 2 units of chloride. Notice the charge on both sides of our arrow are the same. They don't have to be a 0, but they have to be the same. -2 is the charge on the left, and -2 is the net charge on the right. This was called a reduction half reaction. The gain of electrons is called reduction. But however, chlorine is now going to be called the oxidizing agent. Chlorine forced sodium to be oxidized. Sodium forced chlorine to be reduced. So it's really just a matter of flipping the word when you add the word agent. If you're asked to find the reducing agent, really it's another way of asking you, what was oxidized? If you're asked to find the oxidizing agent, it's just another way to ask you, what was reduced? Very important. I would put this little highlighted note in your notepad page, the term agent. Very important to process the term agent and then the vocabulary associated with it. Agents force the other reactant to do the opposite of what it has done. Wherever we've had an oxidation, we must have a reduction. Reducing agents is the substance that was oxidized. Oxidizing agents is the substance that was reduced. By the way, a good another note, agents are always reactants. Let's go on and take a peek at the next slide. The term agents, and I'm just processing this a little bit more. Oxidizing agent gets reduced. It gains electrons. More negative oxidation state. By gaining electrons, you're being reduced. Reducing agent gets oxidized. You lose electrons and become more positive. An easy way to remember that, Leo the lion says grr. Losing electrons is oxidation. Gaining electrons is reduction. Oxidation becomes more positive. To be reduced becomes more negative on the number line. Traditionally, this term agent gets confusing for beginning students, but as I said, just with a little practice, it becomes quite easy. Let's identify the oxidizing agent, reducing agent, the substance that were oxidized, and the substance that were reduced. And we'll just use these following examples, and these are typed out in your notepad page as well. So let me kind of come down and we'll write these out one at a time. Here I have elemental form of iron, FeS, with the elemental form of oxygen, O2 gas. And it's a combination pattern forming an ionic compound, Fe2O3. We'll take a minute to balance this. There we go. Now I know from first year chemistry this is called a combination pattern, but now under this larger umbrella it will also be defined as a redox reaction. Always begin by identifying the initial states of their oxidation numbers. The elemental form of any atom is 0. Iron, oxidation of 0. Here's the elemental form of oxygen, assigned as 0. Oxygen is a -2. Iron becomes a +3 if I simply just uncrisscross this ionic compound. So here I've had iron go from a 0 to a +3, and oxygen went from a 0 to a -2. Iron became more positive, didn't it? The loss of electrons is oxidation. Oxygen became more negative. The gaining of electrons is reduced. Remember the term oxidation, what was oxidized, what was reduced? What are the agents? Always come from the reactant side. Iron was oxidized, and therefore it is the reducing agent. And can I just write RA and we'll get that clear? Reducing agent. Molecular oxygen was reduced, and therefore it is the oxidizing agent. Shall we try another? Here we have Fe2O3, iron 3 oxide, that's in solid form, reacting with gaseous carbon monoxide, and it forms liquid iron and 3 carbon dioxide units in a gaseous form. Did I miss the coefficient? I sure did, right there. A 1:3:2:3 stoichiometric ratio. We're being asked what's oxidized, what's reduced, and then to identify the agents. So step 1, we better figure out what the initial oxidation numbers are. We just worked this guy. Oxygen's always a -2. I uncrisscross here. Iron's a +3. If oxygen is a -2, carbon must be a +2. Elemental form of iron, here's 0. Oxygen's always a -2, gives me a total of -4. So now the carbon has gone to +4. Stand back and look. What's changed in the charges? I noticed iron went from a +3 to a 0. It's going down on the number line. It is getting reduced. Grr, gaining electrons, making it become more negative. Carbon started at +2 and went to a +4. That's becoming more positive. Losing electrons is oxidation, making the element become more positive. So identify what was oxidized and what was reduced. The reactant of Fe2O3 is the oxidizing agent. because iron was reduced. And I'll just use that symbol. The second reactant, gaseous CO, is the reducing agent because carbon was oxidized. I'll give you a moment to process that. We started this journey by just simply assigning oxidation states. With one becoming more negative, there must be going the opposite direction. Carbon became more positive. We have to have one of each. Notice how I grabbed the entire reactant to identify the agent. It's not just iron, it's iron oxide that's the oxidizing agent. It's not just carbon, but it's carbon monoxide that's a reducing agent. I take the entire reactant's formula to identify the agent, and then in that I describe what the element was that changed charge. Here's that last example. In this one I have a little adjustment to make. Could you please make sulfite the polyatomic ion, but it actually carries a -2 charge. In my notepad page I only have it listed there as a -1. Please make that adjustment. We're going to have that with a hydrogen ion, which is a +1. A permanganate ion, which is MnO4 -1, polyatomic ion. Make the same adjustment here. Here's sulfate, but it carries a -2 charge off our polyatomic. We have a water and then a manganese +2. Alrighty, what's change charge? Well, let's start by assigning all oxidation numbers, and these should go pretty fast the more we practice. Starting with the oxygen here, I know it's a -2, so therefore the net negative is -6. It's a polyatomic ion carrying a -2 overall. We made that adjustment there in the notepad. So sulfur must be a +4. Here's a monoatomic ion, so it matches the charge of +1. Oxygen is a -2. There's 4 of them. So manganese here must be starting at a +7. Let's do the product side. Oxygen is always a -2, so I'm now at a total of -8. Sulfur must be a +6. Here's an easy one, +1 -2. And a monoatomic ion matches the charge, so manganese now to +2. What's changed? Here, sulfur was a +4. It increased on the number line to a +6. It was oxidized. Losing electrons make you become more positive. Here's the manganese. Started at a +7, went to a +2. It was reduced. There's the GR part of our half reaction. Gaining electrons is reduction. So let's identify. Sulfite, SO3 -2, because it was oxidized, is the reducing agent because sulfur was oxidized. The permanganate ion, MnO4 -1, is the oxidizing agent because the manganese was reduced. We have now processed some oxidation and reduction reactions by looking at a combination example when sodium combined with chlorine to produce table salt. We then did a second example of a combustion, taking a simple hydrocarbon such as methane and combusting it to form carbon dioxide and water. In this next example, we're going to look at the oxidation of metals by acids. Really, this is nothing more than a familiar pattern called a single displacement or single replacement, where we have an element reacting with a compound. The element in this example will be magnesium, and the compound will be hydrochloric acid. Taking a little piece of magnesium ribbon and dropping it into acid and watching the displacement where hydrogen gas will bubble out of solution. Let's look at this familiar format, this equation, labeling the substances that were oxidized and reduced. We'll find the oxidizing and reducing agents and work towards that net ionic equation. So, in our notepad page, let's begin with the molecular equation of taking magnesium ribbon, which is in a solid form, reacting it with hydrochloric acid, which is aqueous. It is indeed one of our 7 strong acids, so I know it will dissociate. Aqueous ions will form when I go to my ionic equation. Remember the pattern of change? Magnesium is strong enough to displace the hydrogen in our compound. We had something called the activity series in our first year chemistry, and we would know that magnesium is higher up on that activity series, making it more active or strong enough to displace the hydrogen. And so when it does, molecular hydrogen gas will form, and going into solution now is magnesium chloride, MgCl2, based on charge, which will indeed be aqueous. This also is a strong electrolyte. It's an ionic salt. Any water-soluble salt is a strong electrolyte and it will dissociate. Solid magnesium, aqueous hydrochloric acid, gaseous hydrogen, and aqueous magnesium chloride. Let's work to quickly balance this. We'll need to double the HCl to create a balanced equation. Well, let's begin by dissociating. We have magnesium solid, no charge. It's assigned an oxidation state of 0. It's an atom of magnesium. Any element found in its natural state is assigned an oxidation number of 0. Here, however, we have a strong acid, so it's therefore a strong electrolyte, so it will dissociate. We have 2 aqueous ions of hydrogen, AQ, and 2 aqueous ions of chloride. So I broke apart the strong electrolyte, the strong acid HCl. Of course, now we have 2 monoatomic ions, the oxidation number of hydrogen, a +1, and the oxidation state of the chloride ion, a -1. And we have our arrow. We have the gaseous molecular form of hydrogen, H2. Here's an element found in its natural state, so its oxidation number is indeed 0. And we have this strong electrolyte, a water-soluble salt ionic compounds. So we're going to dissociate the magnesium ion, AQ, and the 2 aqueous ions of chloride, 2Cl negative, AQ. So again, here now we have 2 aqueous ions, so the oxidation state of this monoatomic ion matches their charge. Magnesium's charge of +2 and chloride's charge of -1. Let's eliminate the spectators and see what we have. We have chlorides, and that's it, isn't it? Now, to be a spectator, it has to appear exactly the same on the left and the right side of our arrow. Magnesium on the left is a 0. Magnesium on the right is now charged with a +2. Therefore, they are indeed different and will not be eliminated. Hydrogen started as a +1 and went to the molecular form of 0. Notice how indeed we have a change of charge. So let's write that net ionic equation. We have solid magnesium reacting with 2 aqueous hydrogen ions, forming molecular hydrogen in the gaseous form. And now in solution is the magnesium ion, aqueous, carrying a +2 charge. Notice how we can assign the oxidation and reduction half reactions. Magnesium started at 0, went to a +2. Becoming more positive is our oxidation half reaction, the Leo of our Leo-Ger. Loss of electrons, oxidation. Hydrogen went from a +1 to a 0. It is becoming reduced, gaining electrons, reduction, the Ger part of our half reaction. So identify magnesium was oxidized, and therefore it is called the reducing agent. The reducing agent, magnesium solid. The aqueous hydrogen ions was reduced, and therefore they are the oxidizing agents. A very familiar pattern of single replacement, now under the larger category called redox reactions. Metals undergo oxidation by placing them in an acid. We also know other categories of single replacement reactions. I don't have to place a metal into an acid to have a reaction. I can replace that metal into any salt as long as the activity series says that the metal is strong enough or more active enough, the reaction will indeed occur. Now let's take a peek at yet another single replacement reaction by taking iron metal and reacting it with nickel 2 nitrate. We've checked the activity series, and indeed this reaction will occur. Iron is more active than nickel. And let's work this example out just as we did with the previous. Here we have iron metal, so iron written as Fe, and it's in the solid state. We're placing that in with a solution of nickel 2 nitrate. So nickel hooked to the polyatomic nitrate, carrying that +2 charge. So, and the little solution sign will be AQ. Pattern of change, single replacement, iron will indeed displace the nickel, and they exchange their place. So now we have solid nickel in its elemental form, and iron will go with its +2 charge, going into solution, making it aqueous. So this equation will come out balanced as written. Elemental form of iron going to the aqueous iron nitrate. Now let's take a peek at assigning oxidation numbers. Are we getting the idea that nitrate here will be the spectator? Any element in its natural state? Well, let's just go ahead and remind ourselves. This is a strong electrolyte. The aqueous ionic compounds always dissociate. The elemental forms are assigned a 0. The oxidation number of any element in its natural form is 0. Nickel here is a +2. Iron here is now a +2. So here we have solid iron with aqueous nickel carrying a +2 oxidation number, forming nickel in its natural state assigned a 0, and iron now with its +2 charge, aqueous. Notice what's changed. Iron started at 0, went to a +2. There's the Leo, the oxidation half reaction. Becoming more positive is losing electrons, oxidation. Nickel went from +2 to a 0. Here is the GR of our half reactions, gaining electrons, becoming more negative. And notice how I immediately just crossed off the nitrates, knowing that nitrate, the polyatomic ion, nitrate, is the spectator. So I just wrote it in the first reaction and eliminated the spectator in the second reaction and came up with our net ionic equation. So the metallic form of iron, solid, was oxidized. And therefore, we know it's the reducing agent. The term agent is telling me it forced the other reactant of nickel to be reduced. The aqueous ion of nickel was reduced, Daisy. And therefore it is labeled as the oxidizing agent. We saw the change of charge in our single replacement reaction, making it fall under this new category that we're learning called the redox reactions. Now, in single replacement reactions, we're very familiar with having to check something known as the activity series. I hope you still have yours from first year chemistry, but if not, I can certainly make sure you have one. We will always need to check first if the reaction occurs. That activity series lists from the strongest of strong metals down to the weakest, and we just check to make sure the reaction indeed will go. So they're listed in order of decreasing ease of oxidation. So any metal on the list can be oxidized by the elements below it. You try it. And just assume this one will go. If you don't have your activity series, I did not put an example into the note pack that does not occur. I wanted us to practice the redox form of a single replacement. You should pause your video, work through the iron 2 chloride being oxidized by magnesium. Assume the reaction occurs. The answer is yes, it will go. And I want you to write the net ionic equation and identify what was oxidized and reduced and list the agents. Welcome back. Let's check your work. Here we had iron 2 chloride, FeCl2, in solution, so we know it's aqueous, being oxidized by the element magnesium. Magnesium in its natural form is a solid. Magnesium is indeed strong enough to displace the iron, so it's the magnesium kicking out the iron, forming the elemental form of iron, and in solution now, magnesium chloride. So here's the aqueous form here, and this guy will now be a solid. So the two metals exchanging places. Chloride, I can tell, will be the spectator ion. Iron started as a +2. Magnesium was the elemental form, so assigned a 0. On the product side, now it's iron in the elemental form, so it's assigned a 0. Magnesium is hooked by charge, so it is now a +2. So here is my balanced molecular equation. If you've properly identified chloride as the spectator and eliminated it, this is what your net ionic equation looks like. The aqueous ion of iron reacting with metallic magnesium, forming metallic iron, and the aqueous ion of magnesium. Iron went from +2 to a 0. It is being reduced. Gaining electrons makes it become more negative. Magnesium started at 0, went to a +2. It is being oxidized. Losing electrons makes it become more positive. So we've identified our two half reactions, the oxidation and reduction. The aqueous ion of iron was reduced. And therefore we know it is called the oxidizing agent. Metallic magnesium, the elemental form of magnesium, was oxidized, and therefore it is called the reducing agent. If you had that perfect, put yourself an A++ on your notepad paper. It just feels good.
When we think about another pattern of change, this pattern of change is known as oxidation and reduction. I'd like to discuss what this means in this lesson as well. So we're looking at the bottom of page 5, oxidation and reduction. Oxidation we are going to define as the loss of electrons. The reduction is the gain of electrons. When something is oxidized, another must be reduced. They occur simultaneously. A redox reaction is what we'll commonly call redox, an oxidation-reduction reaction. It involves a transfer of electrons from one element to another, a redox reaction. Here's a little helpful little sentence, little game I always say. Just like horses need oats for clear brown eyes, I have a little sentence. Leo the lion says grrr. Leo the lion says grrr. Here's what that means. The loss of electrons is oxidation. The gain of electrons is reduction. That's a little helpful sentence to let me remember those two definitions. Leo the lion says, grrr, Leo, oh, loss of electrons, oxidation. When you lose electrons, we remember that you become more positive on the number line. And when you gain electrons, you remember that you become more negative on the number line. Gaining electrons makes you more negative. Oxidation, loss of electrons, makes you become more positive on the number line. So wherever we have oxidation, we have reduction. And I put a little example of this type of chemistry where I can see a piece of copper wire bent around kind of like a popsicle or wood splint. And it's just sitting into a solution of silver nitrate. So I'm going to show you what I'm seeing. I have a piece of copper wire, so I'm going to add in just that little S to let you know that it's in the solid phase, a piece of copper wire. And it's reacting with a solution of silver nitrate. And I'm going to put in AQ to let you see that it's a solution. So it's not a solid salt of silver nitrate, which are kind of like gray crystals, but it's dissolved in the water. So copper wire is the solid phase sitting in a solution where I've taken crystals of silver nitrate, stirred it up in water, and made a solution. Can you see what's happening over time? There's an observed equation, observed chemical reaction occurring. Notice that the solution is turning blue, and blue is showing that copper is going into the water. You will learn that a nice blue color is copper in water. And what about what's plating out? What do you see starting to deposit on the wire? What are that solid pieces? Well, that's pure silver element. The element of silver is falling out of solution. Here's what we see. The copper displaced the silver, and silver came out as a solid, and the copper went into solution, forming a positive charge. And now it receives the aqueous sign to let you know it's now dissolved in the water. So when copper reacts with silver nitrate to form silver metal and copper 2 nitrate, we have what's known as a redox reaction. And let's show how that occurs. I'm going to simplify this to alleviate, get rid of the nitrate. And I'm going to tell you that the nitrate is a spectator ion. Now, what does that term mean? It simply means that it didn't change in charge. Notice that the nitrate appeared as NO3 minus 1 on this side, and it appears over here as NO3 minus 1. Since it did not change, it's referred to as a spectator ion, and we can just get rid of it in our equation. And rewriting that in terms of showing solid copper reacted with 2 silver ions in solution to form 2 silver atoms in the solid phase and an aqueous copper ion. We have had a change of charge. And that's our very definition of a redox reaction. Let's investigate. Copper in the elemental form is a charge of 0. Copper is not an is not an ion at all. It starts as an atom, and atoms we know are neutral, no charge. On the right side, it formed an ion, and that ion carried a +2 charge. So the half reaction of copper would show copper as a solid, forming a copper +2 ion, and the loss of 2 electrons. You see how this is electrically balanced? +2 and 2 electrons creates a neutral charge overall. This is an oxidation half reaction. Copper lost 2 electrons to go from 0 to +2 charge, an oxidation half reaction. Copper is being oxidized. It became more positive by loss of electrons. Now let's see what happened to the silver. Notice the silver started with a positive charge. It then gained electrons to form the atom of silver. Gaining electron, notice I'm just keeping the electrons lost equal to the electrons gained. This is known as a reduction half reaction. You would say that silver is reduced, making it say that it becomes more negative on the number line. To go from a plus charge to a 0 on the number line, think of it, if you're at a +1 and you go back to a 0, you're becoming more negative. Copper here on a number line started at 0 and went to a +2. That's becoming more positive. Oxidation becomes more positive. Reduction becomes more negative. And to be a balanced redox equation, the number of electrons lost has to equal the number of electrons gained. So we wrote out all kinds of great information here that showed the 2 half reactions where copper and silver changed charges. The changing of charge means it's a transfer of electrons, and that's exactly what a redox is. Copper lost 2 electrons and silver gained those electrons in a redox reaction. Now, one more vocabulary word. If copper is oxidized, and it is, it forced silver to be reduced. So it is called the reducing agent. Silver was reduced, and it was, but it forced copper to be oxidized. So it's called the oxidizing agent. All right, lots of good chemistry there. Let's talk through another practice and really kind of get our feet wet with redox. Here's a next practice, and I tried to give a visual as well. Zinc is placed into a solution of copper 2 nitrate. So here's the element zinc, right? This is just an electrode plate. A hunk of zinc is an electrode, a nice thin piece of zinc metal. Elemental zinc starts as a solid. It's placed into a solution of copper 2 nitrate. Now, I'm going to let you know that the nitrate is a spectator ion. That when it appears unchanged on the left and the right, we're allowed to just leave it out of our equation. So since it didn't change charge, we'll just leave it out and just focus on the 2 metals. Zinc started as an element. Elements are in their natural state, so 0 is its charge. Copper started as a +2 ion. I know so because of the Roman numeral. After time goes by, you start to see the zinc change color in solution. The zinc goes into solution, forming an ion. Zinc is a fixed charge. You need to memorize that. A fixed charge of a +2. And the elemental form of copper now with its 0 as its natural state charge. When zinc started as a solid and went to an aqueous ion that carried a charge of +2, it did so by losing 2 electrons. This is the oxidation half reaction. The loss of electrons. Copper started as an aqueous ion and went to an elemental atom. To do that, it had to gain 2 electrons. To become +2 down to 0 is a gaining of electrons, making it become more negative. This is the reduction half reaction. Now we know to be a balanced redox reaction, the number of electrons lost has to be equal to the number of electrons gained, and it is. They're transferring 2 electrons total. Since zinc is being oxidized, it's called the reducing agent. Since copper is being reduced, it is called the oxidizing agent. There is a transfer of 2 electrons between the element zinc and the aqueous ion of copper through this chemical change. So let's put that into some vocabulary. We said zinc went from 0 to +2. The loss of electrons is oxidation. Copper went from a +2 to a 0. The gaining of electrons is reduction. The transfer of electrons is known as a redox reaction. Redox occurs when you have a change of charge. A compound that is oxidized is known as the reducing agent. And so in this example, zinc was oxidized, so therefore it would be called the reducing agent. And since copper was reduced, it is known as the oxidizing agent. The agents are always on the left side of your equation. Just as what is oxidized and what is reduced, they're always reactants. Agents are oxidized and reduced, therefore on the left side. So a compound that is reduced is the oxidizing agent. The compound that is oxidized is known as the reducing agent. I'd like to try some more practices with you for redox. The oxidation and reduction features really just kind of give us an activity series of how many electrons are lost or gained. And so when I wanted to point this slide out, I just wanted you to see that anytime you see oxidation, notice that the electrons are always on the product side. They are being lost. And notice that for reduction, they always occur on the reactant side because they're being gained. And so loss of electrons is oxidation, Leo. The gaining of electrons is reduction, grr. The placement of the electrons on the left side shows reduction. The placement of the electrons on the right side shows oxidation. To be a balanced redox reaction, electrons lost must equal the electrons gained. So here's an example of rusting. Identify the reducing agent and the oxidizing agent. Any element in its natural state, you know that it's not charged. An atom is neutral, so it has an oxidation state of 0, no charge. The elemental form of iron is Fe as a solid, 0 charge. The elemental form of oxygen is O2, so it's not an ion, it's a molecule, so 0 charge. In the compound now, just think about uncrisscrossing. The iron must have been a +3 and the oxide is a -2. Ionic compounds are built of charges. Remember that the metal will be positive. The nonmetal is always negative. Positives are written first, nonmetals are written last, and you just uncrisscross to find out those charges. So you can see that iron went from a 0 to a +3. If 0 to a +3 is oxidized, it's becoming more positive. The iron is now known as the reducing agent. The oxygen went from a 0 to a -2. Becoming more negative is a reduction. Gaining electrons is reduction. So therefore, since oxygen was reduced, it is known as the oxidizing agent. Iron, the reducing agent. Oxygen was the oxidizing agent. That was all we had to do, is recognize the change of charge and find out, based on oxidation and reduction, label out the agents. Oxidation results in the gain of oxygen, the loss of hydrogen, and reduction is the loss of oxygen and the gain of hydrogen. That's a classic example of an organic chemistry model. Let's see what's changed charge here. Here I have an oxygen in the elemental form as a 0, and now over here I can see it's combined as a -2 in the water. Hydrogen stayed the same. Carbon had to be a -4, and it went to a +4. Identify the oxidizing and reducing agent. Oxygen went from a 0 to a -2, and it did so in both places, so it really did become more negative. Becoming more negative is a reduction process, so oxidizing is the oxidizing agent. And friends, if you can label just one of them, you know the other has to be the opposite term. So the methane is your reducing agent, and the oxygen is your oxidizing agent. That's really all we had to figure out. If this change of charge, let's apply this second rule here. Who gained more oxygen? Well, the carbon did. The carbon had no oxygen here, but it has oxygen here. Gaining more oxygen is oxidation, right? And therefore, it's known as the reducing agent. Oxygen was reduced, and therefore we know it is the oxidizing agent. Oxygen gained more hydrogens. That's reduction. Gaining hydrogens is reduction. Identify the species that is oxidized and reduced in each of these reactions. Write out the half reactions to show how many electrons are gained or lost by the species. You have some practice to do on here in the bottom of page 6. I want you to work through those, come back to the video, and we'll check, and that will be the conclusion then of this lesson on balanced chemical equations and the patterns of change. But stop now, practice this out, and then come back when you're ready to check. Okay, so let's come back. I'll just start with letter A. The element zinc reacts with 2 ions of hydrogen to form the zinc +2 ion and hydrogen gas. So let's pull out the 2 half reactions. Zinc is starting as a solid and going into the aqueous ion of +2. So starting with no charge and going to a +2 charge is a loss of electrons. This is oxidation, becoming more positive. The 2 hydrogen ions started as aqueous ions and turned into the elemental form of hydrogen. To go from a +2 to a 0 required gaining 2 electrons. I should remember to leave room. So +2 electrons. Becoming more negative requires gaining. So this is the reduction half reaction. How many electrons are lost or gained? Well, there's 2. And so in that particular part, we had a transfer of 2 electrons. Zinc lost 2, hydrogen gained 2. And what is being oxidized and reduced also gives you the agents. Since zinc is oxidized, it is the reducing agent. And since hydrogen was reduced, it is the oxidizing agent. Let's try letter B. I'm going to start just by breaking them up into 2 half reactions. Iron started as an aqueous ion of a +3 charge. And on the opposite side, I can see it became a solid iron. No charge at all. So to do that, it had to gain 3 electrons. That's a reduction half reaction. The other element is aluminum. Started as a solid and went to an aqueous ion of a +3 charge. To do that, it lost 3 electrons. We want to keep the charges balanced, so that's an oxidation process. Notice that a +3 and 3 negatives combine to give a 0. So that's what I'm doing. I'm balancing the charge. The aqueous ions will always have the electrons with them. So how many electrons were actually transferred? 3. To balance the charges, there was a transfer of 3 electrons. You can see that in your reaction, iron was reduced, so it is the oxidizing agent, and aluminum was oxidized, so it is the reducing agent. Let's look at letter C. I'll break them apart into 2 halves. 2 iodide ions in aqueous form. Ions are always aqueous. And on the right side, I can see it now in its elemental form of I2. So it became more negative. This had to gain 2 electrons. 2 iodides gained 2 electrons to form a molecule of I2. Remember, the charges always go with the electrons. So this gained electrons, that's GR, that's a reduction half reaction. The next part of that equation gives us the elemental form of bromine, which is actually a liquid. And then on the opposite side, the aqueous ions, the charges here. You know what? I'm wrong, and I'm glad I caught this because look what I did. These negatives, that's a total of -4, and that does not balance 0. And I just noticed that it made no sense to add electrons to negative ions. Ions on side of the charges, if they're positive only, positive charges, because I need to correct this right away. I'm so sorry. Would you mind erasing with me? Thank you so much. And I'm glad I caught this because it made no sense to have negative ions wanting more electrons. And you probably thought, oh, Hanson, you're going crazy. Let's redo this. 2 iodide go to iodine. This right here balances both sides to be -2. That's the correct balance. Now, both sides have the same charge. That's a balanced equation. This now is oxidation. And the next one was the bromine, the Br2, went to 2 Br negative. Well, that means it had to be 2 electrons on this side to create a balanced charge. They're both -2s. And gaining electrons is the reduction half reaction. Ooh, there. So that's correct now in the notes. The gaining of electrons, oxidation there for iodine, reduction for bromine. All right, so that means the I negative was oxidized, so it's the reducing agent, and bromine was reduced, so it is the oxidizing agent. That was C. I think I'll fit in D, silver bromide. So here, AgBr is now giving us the elemental form of both elements. Bromine is a diatomic molecule, so that's why you see it written as Br2, and then we had to go back and balance. Now, break these apart and keep in mind that silver bromide is an ionic compound built of charges. So to break this into its 2-half reaction, ionic compounds, remember these are charged ions. You have 2 silver plus 1 aqueous ions forming 2 Ag. Now this would require gaining 2 electrons, so there's your reduction half reaction. And the negative ion of bromide goes on to form its element Br2, and to do that it had to lose 2 electrons, and there's your oxidation half reaction. Loss of electrons, oxidation, makes the bromide the reducing agent, and it makes the silver the oxidizing agent. And one more, we had zinc and mercury oxide. Let me get that down here. Zinc plus mercury oxide, and it went on to form zinc oxide and mercury. I want you to notice that the oxide did not change charge. It just stayed as the OXIDE oxide. It's O-2, and it didn't change charge. Do you remember that word? That word for something that's in the reaction but did not do anything in terms of changing charge is called a spectator ion. So you can really just get rid of your spectator and rewrite your 2 equations such as this. The elemental form of zinc as a solid formed the aqueous ion of zinc, which was +2, and to do so had to lose 2 electrons. That's an oxidation process. Now, the mercury started as a +2 charge aqueous ion. It had to gain 2 electrons to form the elemental form of mercury, which is actually a liquid at room temperature. That's your reduction half reaction. If zinc was oxidized, it is the reducing agent. If mercury was reduced, it is the oxidizing agent. Oxidized and reduced are patterns of chemical change that show a transfer of electrons.